So the first author, Ahmed Abdelkader, sends his regrets. He had something to do with his PhD program. So the problem we're talking about is conforming Voronoi meshing. So given a piecewise linear complex, we want to place Voronoi seeds such that every input face appears as a union of Voronoi faces. So this is sort of a well-studied problem if you're talking about Delaunay triangulations, conforming Delaunay triangulations. And this is sort of a natural dual to it. But you can't just take a conforming Delaunay triangulation and dualize it and get a conforming Voronoi diagram. They're just not related in that way. So this is sort of a 2D simple example. What I'm talking about is, so the red thing is an input edge, and now I'm going to place these seeds. And you see the input edge was reconstructed as a series of Voronoi edges like that. And then, need some extra ones around the vertices. The way so this problem comes up a lot in generating polyhedral meshes or just Voronoi diagrams where there's some sort of boundary that you're interested in. And most of the time people just clip the Voronoi diagram by the shape of the boundary. And that causes problems like when you have non-convex parts of the input here, you're going to have when you clip it, you're going to have non-convex cells. And you can sometimes just subdivide them further so you have convex cells, but then, okay, well, they're convex, but they're not really Voronoi. You may have lost some important properties. The closest thing that we know of to this is reconstruction with power cells. So the power crust algorithm, it's so great. Aaron talked about this earlier, but the power crust algorithm works by placing seeds along the medial axis or very, very close to it. And then they're actually power cells, not unweighted Voronoi cells. And problem with placing them near the medial axis is there's no extra freedom. So you might want to do something like have bounded aspect ratio Voronoi cells. And so sorry, it's kind of faint here, but I've added extra seeds in the interior. Everything's well spaced so that there'll be bounded aspect ratio to the cells. Whereas with the power crust, you can't add any more seeds or else you'll destroy the reconstruction. Yeah, so as I mentioned at my lab, they sometimes use these polyhedral meshes to do simulations. Here they're doing a fracture simulation where the cracks have to go along the edges. Okay, so our solution is pretty simple, and it's sort of a mostly a theoretical result because we introduced very many seeds for each input feature. But this does set the stage for some more practical work that we're doing at the same time. So given one of these input vertices, we're going to place a small ball around it, and we'll put some seeds on that ball. So vertex will be a Voronoi vertex because it has 4 non-coplanar seeds. And then similarly with an edge, we'll put a circle around it and place some seeds on that circle. The whole edge is now equidistant to those 3 seeds. And then if we have a triangle face, imagine a plane sort of partway out of this sphere, then we'll have pairs of seeds like this to either side of that plane that reconstruct it. So I just want to emphasize again, we're talking about PLCs. As a first step, we're going to triangulate it, but it's not, a triangulation of a smooth closed manifold or anything like that. You can have disconnected components. You can have, an edge with 3 triangles connected, that sort of thing. All right, so this I already talked about, getting a vertex back. An edge, when you go to a face, sort of a curious thing is that you've now introduced an awful lot of Voronoi vertices. So for every triangle in vertex combination, you now have 2 pairs of seeds. So now you have 6 pairs of seeds, 12 seeds for every face. And if you do that, these are the Voronoi faces that you'll divide a triangle into. There's always 6 of them, and they'll be quadrilaterals, or sometimes they degenerate into triangles. And the first author, Ahmed, has a nice little applet online. You can move the points around and see what kind of Voronoi cells you get. So the hard part is showing when is this sufficient? When is this going to work? We're going to start with assuming that all the radius of the vertex spheres are 0, and same with the edge circles. And that way, all the seeds are going to be infinitely close to the input vertices. So the key is to show that when you're generating the Voronoi faces for a triangle, the only seeds that matter are the ones that were around the vertices of the triangle. And so what that translates into is these empty ball neighborhoods. You need that there's no other input vertices inside these empty balls. And so this is the it's the union of all maximal empty balls inside a triangle, but you can describe that just by 4 of them, just the diameter circles of the edges, and then the smallest enclosing sphere of the whole triangle. So this should remind you of nonobtuse triangulation. And indeed, if you have a planar triangulation or one that's nearly planar, all you would need is a nonobtuse triangulation, and then this reconstruction would work. For 3D, we need some extra things. We need to do some extra refinement based on something like the local feature size, and then we also need some extra seeds. And unfortunately, the method we have in the paper, the number of seeds we introduce is very large and depends upon the geometry of the complex, not just the number of triangles, but combinations of the angles on these feature sizes. All right, so and actually you don't quite need nonobtuse. You can propagate the nonobtuse refinement. You would split these 2 triangles, or both of these triangles into 2 triangles by introducing a vertex somewhere here. We don't actually have to introduce a vertex. We can just introduce a pair of seeds, but you can more or less think about it as first you generate a nonobtuse triangulation. And then suppose we have a triangle, and then there's a disjoint input edge that comes close to it. We're going to do uniform refinement on the nonobtuse triangles so that these the balls of the refined triangles don't come anywhere close to the other input edges and vertices that aren't part of either of those 2 triangles. So if the triangulation is flat, meaning you have nonobtuse dihedrals between triangles, that would be all you needed. But if you have sharp angles, here I've tried to draw a triangle and then a edge coming out like this with making a sharp angle. When we introduced seeds on the circle, the edge circle, these are now going to be the closest seeds to some points sort of in the middle of the triangle. And so now we need to add some extra seeds there. And to sort of keep this from propagating back and forth as you move away from the vertex, you might have to refine the input edges outside the vertex seeds. You might need to refine them into something about the same size as the edge circles that you use. And this is very similar to what's been done for Delaunay refinement. Okay, so that was all for if you're assuming that the vertex spheres and the edge circles were radius approaching 0, but we'd like to actually compute these things, and so you'd like strictly positive radii. And so the theorem is that it's always possible, but again, the level of refinement it can be quite high. So the first thing to notice is that the empty neighborhoods you need change. So here I have the 0 radius case, and now I've blown up the vertex balls. All the seeds are going to be on the surface of the vertex ball. And like this edge circle, before I needed to exclude the input vertices, but now I just need to exclude these seeds here. So good news is as you increase the vertex ball radii, the empty ball neighborhoods you need get smaller. The bad news is as you increase the edge circles, this point spreads out into a number of co-circular vertices, then these diameter spheres grow back out a little bit. And the sort of the worst case setting is that there's a fourth vertex sitting out of the plane here that's just above the purple sphere. And as you grow the radii, the vertex sphere radii, the purple sphere shrinks, but the vertex sphere around the fourth point here grows, and then they start to intersect. And so you need yet more refinement beyond the sort of non-obtuse condition we had previously. All right, another different direction now is, can we reduce the number of Steiner points? It seems like kind of overkill to have 12 Voronoi cells for every single triangle. So the first observation is that if you grow the edge circles so that they overlap, then you can use the same pair for both edges at each triangle vertex. So if you do this, now you only have one pair for every vertex of every triangle. So that's half as many. And then the other thing you can do is, well, you can make these vertex spheres really big so that they overlap, and now the edge circles are common for the two vertices of the edge. There's just one circle. And if you kind of think about doing both, then for every triangle you just have a triple overlap of 3 spheres. The surface of the spheres will have 2 points in common, and those 2 points are where you want to put your Voronoi seeds. And so this is great. You only have 2 seeds per triangle, and that's the sort of 3D view of that. And it's that last thing that is really what we're working on as a practical expression of this idea. We just have those triple intersections, and so the paper is about how do you sample a smooth manifold so that, and how big do you make the vertex spheres so that all you have are these triple intersections. All right. So in conclusion, any PLC can be represented as the union of Voronoi faces in the real Voronoi cells. They're not power cells, not clipped or restricted or anything like that. And this result isn't particularly practical because of the huge number of seeds you get, but we think it sort of points the way towards that. So one of the open problems is just, so recently there was a result for 2D planar straight line graphs that you can divide those into a non-obtuse triangulation using n to the 2.5 vertices. And we're not going to do, getting non-obtuse is one step in our refinement, so we're not going to do better than that until that bound is improved as well. All right, that's it. Yeah.
So when you just cut a single plane, each one of the single plane, then you have this symmetry right?
Yes.
So you end up with all these degenerate situations. Your image provided.
Oh, yeah, right.
That degeneracy will become a problem.
I'm not sure. So I guess whether it's a problem or not depends on your context. But yeah, or maybe I should go back to the triangle pictures. So yeah, so what you're talking about, right? I mean, here, yeah. So here, right? So there's a this vertex is degenerate. You have these three Voronoi edges in the plane of the triangle, but then there's also at least two more, one going in and out. So you have all these high degree vertices, and then at the input vertices, yeah, they're going to be very high degree Voronoi vertices as well. And we did use that code Voro++ to compute the Voronoi diagrams, and it seemed to handle these degeneracies just fine. But yeah, it depends on your implementation. I think that code works by clipping the Voronoi cells by separating planes. So you start with this big infinite object, I guess, and then you slice off plane. I think the codes where you form the Delaunay triangulation and then dualize it, they would probably have more troubles with the degeneracy. All right, thank you.